Welcome to the switching theory and logic design class. In this class, we are going to see the concept of comparators. Okay. So coming to here, what is meant by a comparator? The comparator definition. See here, the comparator is a comparison of two numbers. So see here, this is very important. The comparator. The comparator is compares two numbers, that is an operation that determines whether one number is greater than or less than or equal to the other number. So it will compare two numbers. From the first number it will check the other number is a lesser one or greater one or equal one. So see here, I have given two numbers here, that is A and B. I have given two informations. So this two information it is comparing. So some hardware is available under this comparator and it is giving the three outputs, A less than B, A equal to B and A greater than B. So see here, if you are given 5 and 7, it will give the comparison between 5 and 7. So 5 is less than 7, 5 is less than 7. That is, if you are giving A, B, that is A is less than B. So A is less than B is going to active, that is the output of the A less than B position is going to switch on condition and remaining two conditions are going to switch off conditions. So this is a normalized block diagram for the normalized comparator. So this is a normalized comparator. So now coming to see here, single bit comparison. So here I am taking A as a single bit and B as a single bit. So A may be 0 and B may be 0. Otherwise it may be 0 or 1, and it may be 1 or 0 and it is 1 1. So these are the maximum possible combinations for comparing A and B values. Okay. So A is consisting of 0 or 1 and B is consisting of 0 or 1. So here if it is 0, so see here, if A is equal to 0 and B is equal to 0, then what is the result? A equal to B or A less than B or A greater than B. So here coming to the values of this A and B both are same. So for that reason the output A is equal to B is going to active state and remaining two conditions are going to deactivate state. So let us come to here. First we will see these three combinations. So first coming to here, A greater than B, A greater than B. So when A is greater than B, see here A value is equal to 1 and B value is equal to 0. So this is the combination. So this is the combination, you can observe that. This is the combination, you can observe that A has greater value and B is lesser value. That is, A is greater than B. So for that reason, here I am mentioning this output. So A is greater than B. So A is greater than B is equal to 1 and remaining all the combinations are, I am giving as 0. Right? Okay, right. Next coming to here, A equal to B and A less than B. So see here, it is very simple thing. When A is equal to 1 and B is equal to 0, see here the A is greater than B condition is going to activate state and remaining two are in the not activated state. That is, the output is 0. Next, coming to here, the second combination, that is A equal to B, A equal to B. So in the A equal to B condition here we have, so A value is 0, B value is 0 and A is equal to 1, B is equal to 1. For these two combinations, here A equal to B, so this is the A equal to B operation. For A equal to B, those two are 1 and remaining combinations are 0. And next coming to the A is less than B. So A value is 0 and B value is equal to 1. So A is less than B, right? Because B is the bigger value. So at this situation, A is less than B is going to activate situation and remaining are a deactivated situation. So these are the comparisons and their outputs for the binary inputs of given informations for A and B. So it's very simple. A and B we are comparing and we have given the outputs. Now write down the Boolean functions for these three combinations. So the first one, A is greater than B. The first one, A is greater than B, that is equal to, so A is greater than B, when it is going to on, when you can say, check that, so A and B bar. So this is the expression for A greater than B. So for example, consider this is the output Y. Y is equal to AB bar. Okay, next, A is less than B. So check that second combination. So this is the situation, that is A bar B. A bar B. Next, the third situation, A is equal to B. This is the third combination. For this combination, what is the output? See here, AB plus A bar B. So this is the condition A bar B bar. This is the condition AB. So A bar B bar plus A. So these are the three expressions for the comparator, for a single bit comparator. So A is single bit, B is single bit. So two single bits I am comparing. So this is called single bit comparator. For the single bit comparator, we have three outputs: A greater than B, A less than B, A equal to B. A greater than B is equal to AB bar, A less than B is equal to A bar B, A equal to B is equal to A bar B bar plus AB. For this circuit, you have to draw the diagram. So see this one, this is seems to be like as XNOR operation. This is seems to be like as XNOR operation, that is reverse of XOR gate, reverse of XOR gate. So this is representing XNOR operation. This is, you can write like this: A exclusive or B whole bar. Otherwise you can write A exclusive XNOR B. A XNOR B. Okay, so A XNOR B operation we are representing in this way. Okay, right. So am I erasing everything? Right. Now we have to draw the diagram for this one. So see here, I have drawn the diagram here. So here, this is the diagram is representing the three conditions. So coming to see here, A input, B input. This is the A input and B input. Here we have A bar. Here we have B bar. So B bar. So see here, for this indicator, A bar signal we are giving and B signal we are giving. So finally this is A bar B. So this is A bar B. So this is A bar B. And this is A B bar. A B bar. A B bar. Okay. So see here, A bar B, A B bar. A bar B I am giving to here A less than B. A B bar I am giving here A greater than B. Okay. So this is very simple operation. So see here. So this is A bar and this is B bar. So this is B bar and this is A bar. So here I have to give, see here, this is A bar. So the output of this AND gate is A bar B. And here I am using another AND gate. I am taking the A signal here. So now the answer is A B bar. A B bar. Right? I said that. So see here, these two conditions, that is one is less than, one is greater than. And what is the A equal to B? So A equal to B is nothing but as XNOR operation, that is implementing XNOR operation, that is nothing but as a reverse of XOR gate, reverse of XOR gate. Actually see here, A bar B plus AB bar, A bar B plus AB bar. So I am adding these two values. So here I am adding these two values. So that is I am using a OR gate. So here the OR gate output is A bar B plus AB bar. Okay. So reverse of this OR gate is nothing but as, reverse of this OR gate is nothing but as A XNOR B. A XNOR B. So here I am taking excluder function. See here, we know that XOR B function is equal to AB plus AB bar. XOR function, that is Y bar, is equal to A bar B plus AB bar whole bar. Okay, so see here, this AND gate A bar B I am taking here, and this AND gate AB bar, this AB bar I am taking here. Okay, so these two I have to sum. So for that reason I have used OR gate. So for this total sum I have the bar. So this bar I am representing with this bubble. Okay, this bar I am representing with this bubble. The same diagram I have drawn here. So see here, this is the NOR gate. This is the NOR gate. So this is the diagram which explains the three conditions of a comparator. So for our comparator we have three outputs, that is A less than B, that is A greater than B, that is A equal to B. So this is the diagram for a single bit comparator. Note it down carefully. Everyone, note it down carefully. Right. So this is the single bit comparator. This is the single bit comparator. So this is the logic diagram for single bit comparator. Okay, right. Let us move to the magnitude comparator. Here we have a special name called magnitude comparator. What is meant by magnitude? Magnitude is nothing but as the weightage of the given word, otherwise the weightage of the given number. Okay, so here most of the times we are saying that magnitude comparator, magnitude comparator. So this magnitude comparator is starting for the 2 bits. So if A is equal to, you are taking 2 bits, and B is equal to, you are taking 2 bits, then it is called magnitude comparator. Okay, that means, for example, take A is equal to 00011011, and you take B is equal to 00011011. That is, A is consisting of 2 bits, B is consisting of 2 bits. So for these 2 bits you have to compare. So see here the definition of magnitude comparator. A magnitude comparator is a combinational circuit that compares the two numbers A and B and determines their relative magnitude. So it finds the relative magnitude separately, and the outcome of the comparator is specified by 3 binary variables that indicates whether it is A less than B or A greater than B, A equal to B. So this is very simple operation that we will see now. So for in that first we will see the 2-bit magnitude comparator. Okay. So see here I am taking A is A0 A1. So here I am taking A is equal to A0 A1 and B is equal to B0 B1. That is, I am taking 2 bits for each input. For each input I have 2 inputs. Each input is consisting of 2 bits. Now see here A is equal to A0 A1, that is A0 A1. That is I am taking 00011011. So this is the A bit, and coming to the B bit, B0 B1. Okay, B0 has a 00011011. So this is the A possible combination, these are the B possible combination. Now you have to compare these two. What are the maximum possible combinations you can compare in between A and B? So see here, from this 00, you can compare first 00, and you have to compare 01, and you have to compare 10, and you have to compare 11. So now what is the task you have to do? First take the A combination where A is equal to 00, right? A bit is equal to 00. Then check the B bits. So for 0000 compare, that is nothing but as A equal to B. 0001, that is A is less than B, that is B is the bigger value. So the third combination and the fourth combination. So like that, so 00, this is the A value, and coming to the B value 00. A is equal to 00, B is equal to 01. A is equal to 00, B is equal to 10. A is equal to 00, B is equal to 11. So for 00 combinations you have to take 4 combinations of B. Now take the 01 combination. So 01, 01, 01, 01. Here again 00, 01, 10, 11. So see here. So the B combinations. So the B combinations, all the B combinations we are verifying with each combination of A input 00 and 01, next 10 and 11. Like we are comparing for all the combinations of A and B. A and B. Next coming to that 10 with 4 combinations. Next 11 again with 4 combinations. All the combinations we are verifying here for the A and B. Like that. And now I have drawn. So now that, so see here, first I have taken A is equal to A0 A1, 0001, sorry, 000000, 4 combinations of these 00s, and 4 combinations of 01, and 4 combinations of 10, and 4 combinations of 11. Next coming to here B. So B has 00011011. 4 combinations we got. The same 4 combinations I am repeating here. Here also I am repeating. Here also I am repeating. So all the 4 combinations I have repeated here. All the 4 combinations I have repeated here. Okay, next coming to that, these are the output combinations. So A greater than B, A equal to B, and A is less than B. So these are the maximum possible combinations. So see here, first what is the value of A? 0, 0 and B is equal to 0, 0. For these two you have to compare. How to compare these two? So see here you have two bits, here you have two bits. How to compare? So by combining A, so these are the two values, A not A1, we have two values, but you have to say the finally A value. Here also B not B1 is there, you have to say final B value. 0, 0, that is the value is 0, that is A is equal to 0 and B is equal to 0. A is equal to 0, B is equal to 1, A is equal to 0, B is equal to 2, A is equal to 0, B is equal to 3. Here the 3 indicates 1, 1. The 3 indicates 1, 1. So this is called magnitude comparator. Otherwise, you can compare like this also. You can compare A naught, B naught. So A less than B naught, A less than B naught, A naught less than B naught, A naught less than B1. You can compare this also, but these all are not magnitude comparators. That is also valid comparator, but that is not magnitude comparator. So the magnitude comparator is like this. You have to take the complete A value, you have to take the complete B value. Like that you have to compare. So here our topic is 2-bit magnitude comparator. A is 2 bits and B is equal to 2 bits. Okay, right. So now check that. A is equal to 0, B is equal to 0. That is A equal to B. That is A equal to B. That is the first combination. Next, A is equal to 0, B is equal to 1. That is A is less than B. That is A is less than B. So this combination is going to on. So the remaining two combinations also, A is 0, but here A is equal to 1, A is equal to 2, A is equal to 3. But this 3 combination, A is less than B is going to 1 and remaining A greater than B, A equal to B combinations are going to 0, 0. Okay, right. Now here we have to take 0, 1 combination. 0, 1 is less than 0, 0. That is 1 is less than 0. Is it right? No. 1 is greater than 0. So for that reason A greater than B equal to 1. Next, here 1 is there, here also 1 is there. So for that reason A equal to B. A equal to B. And next 1, 2. 1 is less than 2. So for that reason this is going to 1 and this is going to 1. Right? So like that you have to draw the complete table. Like that you have to draw the complete table. This is the comparison between two numbers. That is here we are representing with orange color table and green color table. Orange color table consisting of A values and green color table is consisting of B values. And next coming to this table, it gives all the combinations results for A less than B, A greater than B and A equal to B for the A and B inputs. Right. Now you have to write down the formulas for these 3 outputs. So A is less than B, A is greater than B, A equal to B. For these 3 combinations you have to write down the outputs. So see here I have written A greater than B is equal to, so see here the first combination A greater than B. For A greater than B, whenever the value of this A greater than B is equal to 1, check that 1 and identify the input combination. So A greater than B, here it is 1. So the combination of 0, 1, 0, 0, this seems to be like as a 4 value. The min term, check that the min term. So 0, 1, 0, 0. So I have written this A and B combinedly. So the input combination, otherwise you can represent this one A bar B. So see here A bar B, C bar, D bar, like that. So here A naught bar, A1, B naught bar, B1 bar. So that is the min term which is representing M4. That is a min term which is representing M4. The M4 I have written here. So this is the M4 value. This is the M4. Like that, see the remaining combination 8, 9, 10, 11, 12. 8, 9, 12, 13, 14. So these are the combinations. This one and these 3. So these are the combinations. Like that I have written A equal to B function also, where A equal to B. A equal to B is equal to sigma small m of 0, 5, 10, 15. Only 4 possible combinations. Here we have the maximum 4 combinations are 4. 4 are equal to 4 combinations only. So the 4 combinations we have represented with A equal to B. So these are the 3 combinations. For these 3 combinations we have written. A is less than B. That is a sigma 1, 2, 3, 1, 2, 3. And next the remaining values that is 6, 7. And we have one more value that is 11. So these are the maximum possible min terms for A is less than B. Okay, note it down. Next, coming to here, we have to simplify these three equations. We have to simplify these three equations. So the first equation is a greater than b. Now I have drawn the Karnaugh map for a is greater than b. So for a is greater than b, 4, 8, 9, 12, 13. So 4, 8, 9, 12, 13, 14. So all the one elements I have represented here, and I have formed a quad group here with red color box, and I have formed two pairs with green color box and yellow color boxes. So those results I have written here. So a is greater than b is equal to a naught b naught bar plus a1 b naught bar and b1 bar plus a naught a1 b1 bar. So like that we have formed the 2-bit magnitude comparator for a is greater than b combinations. Next, coming to here, this is the next combinations for a equal to b. Here for a equal to b, 0 and 5 and 10 and 15. So these are the four combinations. Is there any possibility to make group? So it is not possible. We cannot make group for these four ones. It is not possible. Why? Because horizontal groups are allowed, vertical groups are allowed, but here no groups are allowed. So you have to write down the four minterms as usual. So these four minterms are representing nothing but as x naught function of these four input variables. So that is a naught x naught, a1 x naught, b naught x naught and b1. Simply you can say that is a equal to b is nothing but as a x naught b, a x naught b. So I have written detailedly that is a naught x naught, b a1 x naught, b naught x naught and b1. So this is the a equal to b operation. Okay, right. Next, coming to the third combination. For the third combination, a is less than b. For a less than b, 1, 2, 3. So see here 1, 2, 3. Next 6, 7. 6, 7. Next 11. So these are the ones we have represented. For these ones, we have framed the one quad group and two pair groups. The one quad group is representing a naught bar, b naught plus a naught bar, a1 bar, b1. So that is the representation for this. Right, this green color box. For this green color box, a naught bar, a1 bar, b1, and this yellow color box, a1 bar, b naught bar, b1. So this element and this element we have framed with yellow color group. And see here, this is a naught bar, a1 bar, a naught bar, a1, a naught, a1, a naught, a1 bar. So this is the order we have written based on gray coded information. So this is a finalized expression. So you have to analyze these quads, how we have formed quads. So here I am explaining and I have drawn the complete information. Now you have to open your notebook and draw these three Karnaugh maps. Alright, whatever the minterms I have mentioned here, for these minterms you have to draw the K map. Okay, so first draw the K map and solve by your own. Then draw the logic circuit diagram, logic diagram. Okay, so here I am doing everything. I will get all the information. But when you will do this examples by your own, then only you can write your exam perfectly and you can design your hardware perfectly. That is very, very important. Right. Now coming to the finalized three Boolean functions, the minimized Boolean functions I have mentioned here. These three are the finalized Boolean functions. These three are the finalized Boolean functions. So these Boolean functions we have drawn like this. So see here, I have taken a naught bar line, a naught line and a naught bar line, a1 line and a1 bar line, and b naught line, b naught bar line, b1 line and b1 bar line I have taken here. So the first function, a naught, b naught bar. So see here, a is greater than b. So this is the first combination. So this is the first one. So this is the first one. So see here, this is the first one, a naught, b naught bar for a. So see here, a is greater than b, a is greater than b. For this combination, the first one, a naught, b naught bar. So see here, so it consisting of two inputs. The first input is a naught and the second input is representing b naught bar. So that is a naught and b naught bar. So here I have written a naught, b naught bar. Next, a1, b naught bar, b1 bar. a1, so see here a1, this is the a1. and B naught bar, B1 bar. So this is the B naught bar and this is the B1 bar. So this is the function A1, B naught bar and B1 bar. So that is the next product term. Coming to the next product term, A naught A1. So see here, A naught A1, next B1 bar. So this is the B1 bar. So this is A naught A1 B1 bar. So these are the three product terms we are representing with three AND gates. These are three AND gates I have connected to an OR gate. That is I am making the plus operation. That is the OR gate operation I have mentioned. So this is the A greater than B combination. Right? In the same way, A equal to B diagram and A is less than B diagram. For A equal to B diagram, I have taken two XNOR gates here. I have taken two XNOR gates here. These two XNOR gates I have connected to here. You have simplified the final expression, you will get like this. For A naught A1 we have performed XNOR operation. For B naught B1 we have performed XNOR operation. These two XNOR operations we are multiplying. So that is the A equal to B combinations we have represented. Okay, it's very simple thing, but you have to work out. Okay, so this is the final function for A equal to B. Right. Next, 4-bit magnitude comparator. Next we will see the concept of 4-bit magnitude comparator. So coming to here, the 4-bit magnitude comparator. So this is the generalized block for 4-bit magnitude comparator. Here I have taken two words of A. So two words for A and B, where A is equal to it consisting of 4 bits and B is consisting of 4 bits. So it is nothing but here we have 4 binary inputs, here we have 4 binary inputs. Each binary input consisting of 0 or 1. So for that reason here the maximum possible combinations are 16. Here also for word B, it is also consisting of the maximum possible combinations of 16. So here 16 combinations are available, here 16 combinations are available. So here for the first combination of these 4 digits, you have to compare with the 16 combinations. So here 0, 0, 0, 0. So this is the first combination. 0, 0, 0, 0, 0. So this is the bit A. So here for you have to check this 0. This A0 with this B bit, B possible combinations from 0, 0, 0, 0 to 1, 1, 1, 1. So all the 16 combinations you have to compare with this 0, 0, 0, 0. Like that each combination of A, you have to check with all the combinations of B. So totally you will get 256 comparison statements for this A and B. So totally you will get 256 combinations of comparisons for this 4-bit binary comparator. Okay, so here I am not drawing all the combinations, so see carefully. And so this is the 4-bit magnitude comparator and it has 3 outputs. Those 3 are A less than B, A equal to B, A greater than B. So it may be single bit comparator, it may be 2-bit comparator, it may be 4-bit comparator, it may be 8-bit magnitude comparator or 16-bit magnitude comparator, whatever it may be. Whatever it may be, it has only 3 outputs. It has only 3 outputs. So here, how to compare the these 4 bits and those 4 bits? Okay, comparison is not a big problem. You can draw the table by sitting nearly 2 to 3 hours. You will complete that complete table. But here the question is that logic diagram or the hardware diagram. How to implement the hardware diagram based on the truth table? You will get 3 outputs. You have to draw the K map for the 3 output functions and you have to solve. This will take a lot of time. So for that reason, we have taken an alternative path. So first see here, how will you compare 2 bits? So here I have A bit. So word A, that is A3, A2, A1, A0. Here B3, B2, B1, B0. That is A word is available, B word is available. How will you compare? How you will compare these 2 bits? Okay, these 2 numbers. So I have taken an example. So see here, 1100. This is the A bit. And next coming to the 1000. Okay, this is the B bit. So in these 2 combination, which one is the in these two combination, which one is the bigger one, which one is the lower one, right? You have to check that. So here you can say 8 plus 4 plus 2 plus 1, like that we are doing 8 4 to 1 code. Here we have 8 4, that is equal to 12, and here we have only 8, right? So this is 12, this is 8. So A is bigger one and B is the lesser one. Like that we are saying, based on the decimal values we are saying. So see here, I want to say one more clarification. Here, which bit has more weightage? Here, which bit has more weightage? That is, LSB bit has more weightage or MSB bit has more weightage? You have to know why, because you are comparing. When you are comparing, you have to know the weightage of LSB bit and weightage of MSB bit. Which bit has more weightage? So here I said that 8 4 to 1 code. So the LSB bit is the weightage of 1 and the MSB bit has the weightage of 8. So in these two bits, which one is the more weightage? Right. Very good. So the MSB bit, right? So here MSB bit or LSB bit? The MSB bit has more weightage. So this MSB bit has more weightage. So that is the very important one. Okay. So first you compare these two. Okay, first you compare the first two MSB bits. If these two bits are equal, then go with the next MSB bit. Okay, right? Next MSB bit you have to check. Like that you have to check and you have to decide the which one is bigger one. So for this operation we have to make the hardware implementation. So see here, I have taken one more example. A is equal to 0 triple 1 and B is equal to 1 triple 0. Right? So here I have taken two combinations. So the first one 0 triple 1 and B is equal to 1 triple 0. The value of this one is equal to 7. The value of this one is equal to 8. So you can say 8 is bigger one and A is a lesser one. So that is A is less than B. So A is less than B is equal to 1. But now we have to write a program. Otherwise we have to implement the hardware. So for that first you have to check the first MSB bit. First you have to check the first MSB bit. So what is the MSB bit here? That is B3 and A3. So if B3 and A3 if you compare, if you got any difference, that is if B3 is good one, otherwise if A3 is greater one, then you have to give the result. So first check A3 B3 bits. If is there any difference, here A3 is equal to 0 and B3 is equal to 1. Obviously, A3 is less than B3. A3 is less than B. So then there is no necessity of checking the remaining bits. There is no necessity of checking the remaining bits. So see here, the remaining bit, all the bits are 1, but the value is equal to 7. Here all the bits are zeros, but here the total value is equal to 8. So the MSB bit decides which word is the bigger one. So there is no necessity of checking the A2, B2, A1, B1, A0, B0 bits. Okay, right. Next, see here 1 triple 0 by using 8 4 to 1 code and 0 triple 1 8 4 to 1 code. Okay, you can compare like this. So first we are analyzing the operation, then we will see the hardware implementation. So finally we can say that A is less than B. So now you will take one more example. So in this example, A is equal to 1101 and B is equal to 1000. Okay, here A3 3 bits are same. So see here, first check A3 B3 bits. If these two are equal, then check A2 B2 bits. So first check A3 B3, then go with A2 B2. So here A2 B2, where A2 is equal to 1 and B2 is equal to 0. So here you are checking again MSB beta. If these two bits are, if you compared, then any bit has gained more weightage, then decide that word is the bigger one. Here A2 is equal to 1 and B2 is equal to 0. So say that A is the bigger one. Why? Because A plus 4 is equal to 12. So here A plus 0. So here after 12 you saw also 1, then you will not get 12 value. You will get 11 value only. So for that reason, so this is the bigger one. Okay. So see here, A2 is equal to 1 and B2 is equal to 0. So that A2 is greater than B2. No rest of checking the remaining A1, B1 bit and A0, B0 bits. So the answer is A greater than B. Next, take one more combination. So A is equal to 0 triple 1, B is equal to 0 triple 1. Now how you will compare here? So for this case, first check A3, B3. I am checking A3 and B3, both are same. Next check with A to B2. I am checking A to B2. A to B2 also same. Here it is 1, here it is also 1. Next check A1, B1. Here A1 is equal to 1, B1 is equal to 1. Okay, both are same. Next then check A0, B0. A0 is equal to 0, B0 is equal to 0. So in this combination, all the bits of A is equal to all the bits of B. Now you can say this is A equal to B. Now you can check that this is A is equal to B. So this is called 4-bit comparator. This is called 4-bit comparator. So based on this operation, we are implemented the hardware for the 4-bit comparator. So coming to here the 4-bit comparator. So see here I in the previous process. In this process, first I have compared A3, B3, then I have compared A2, B2, then I have compared A1, B1, then I have compared A0, B0. So the comparison process is different from the previous discussion to present discussion. But final the result we are giving the an accepted result. Okay. So for that reason, see here, individual bit comparisons are required. So for comparing this one, we need a single bit comparator. Here also we need a single bit comparator. Here we need a single bit comparator. Here we need a single bit comparator. Okay. If this when you are comparing A3, B3 bits, if you get the result either less than or greater than, directly you can say this is the A is bigger one. Otherwise you can say B is bigger one. Otherwise you have to go for checking A to B2. Okay, like that you have to do the operation. So here I have taken. So see here. First I am comparing. So first I am comparing A3, B3 bits. So first I am comparing A3, B3 bits. Okay. So if A3 and B3 bits I am giving here. So if A3 and B3, if it is giving the result either less than operation or greater than operation. Okay. So this is the equal to operation. Where X3 is I am represented here. So here I am representing the X3. So this X3. If X3 is equal to 1, the meaning of this one is A3 is equal to B3. If X3 is equal to 1, then A3 is equal to B3. Otherwise, if you got 1 here, if you got here 1, if the line is equal to here, it is 1, that is A bar B. A bar B, if it is equal to 1, this is A bar B. That is A is less than B. If this line is going to 1, that is A less than B. If this line is going to 1, this is A greater than B. If this line is going to 1, that is A equal to B. That is A equal to B. Right? So these are the 3 output operations. So here, except this X3, except this X0 output, for the 2 remaining combinations, you can say that if A is bigger one or B is bigger one. Here, when X3 is equal to 1, you can't say. You have to check for the remaining combinations. So see here, if A is less than B came, when this line is equal to 1, this is I have connected to an OR gate. So irrespective of remaining circuit. So by seeing this circuit, you will get a lot of fear. So don't get fear. So neglect this complete circuit. If A is less than B, then this line is equal to 1. This OR gate is connected to this line. If it is equal to 1, automatically the OR gate is equal to 1. Why? Because any one of the input of the OR gate is equal to 1, automatically the OR gate is output is equal to 1. So here if it is equal to 1, directly this OR gate is going to 1 and remaining 2 outputs are going to 0. Okay, so see here, A less than B, A greater than B, A equal to B. 3 outputs I have written here. So see here, this is A less than B, and this is A greater than B, and this is A equal to B. So these are the 4 combinations, 3 combinations. These 3 combinations we are represented here. Okay, so here the first bit, when you compare these first two bits, you will get either this value 1 or this value 1. Okay, if 2 bits are, you got 1, 1, then you can say the A is bigger one or B is bigger one. When you got X3 is equal to 1, when you will get X3 is equal to 1, then, so see here, the deciding parameter, is there from this AND gate, otherwise this AND gate. These two AND gates will decide the answer. So here x3 a3 is equal to b3 is equal to 1 1. So here a to b2, if a to b2, when you are comparing a to b2, if a2 is less than b2, this line will activate. If a2 is greater than b2, this line will goes to activate. So this line will connect it to the OR gate whenever a3 is equal to b3. So a3 line b3 line I have connected to here for the AND gate, and when it is when this AND gate for the AND gate, if the both inputs are 1, then only the output is going to 1. So here all the single bit comparators are working parallelly. All the single bit comparators are working parallelly. So here you will get the same value. Then it will for this AND gate, the one of the input is equal to 1, and next it will check the A to B combinations. If it is giving the result A is less than B, this AND gate output is goes to 1. Otherwise, this AND gate output is going to 1. Otherwise, here we have written x2. x2 is going to 1. Okay. So like that, you are saying 3 operations. So these two combinations are connected to this AND gate. Then it will check 2 conditions. The first condition, a3 is equal to b3. Then after that it will check a3 is less than b. So a3 is less than b is right. Then this AND gate will give the 1. This AND gate 1 is connected to this OR gate. So whenever this AND gate is equal to 1, automatically the OR gate output is also 1. Why? Because the OR gate input is connected to this AND gate, and it will say, and it will tell that here the comparison of a is less than b is equal to 1. Why? Because one of the input for the OR gate is equal to 1, automatically the OR gate output is equal to 1. So see here from the A3, B3 bits, I am giving the value directly. That is a very simple thing. Now I am comparing A to B2 values. These A to B2 values are accepted whenever x3 is equal to 1. That is the combination. Okay. For that reason, here we have 2 inputs. Next, A1, B1 I also am comparing. It is also giving the outputs. But whenever these values are considered, whenever these A3, B3 bits 1 and A2, B2 bits 1, then only it will consider the outputs of these two signals. Okay. Next, coming here, this last combination of A1, B1. If these 3 bits are equal, when comparing A3, B3, if it is equal to A3 equal to B3, and if A2 is equal to B2, when it is equal to A1 equal to B1, and finally it will check the A0, B0. If this is also equal to 1, then only the final AND gate goes to 1. Then finally you can say A equal to B. Then finally you can say A equal to B. So these are the 4 maximum possible combinations. It is very simple theory, but you have to concentrate you have to put more concentration. It is very simple. It is completely logic oriented. This is completely logic oriented. I will share this PPT to you in WhatsApp group. Then you have to check it. So this is the 4-bit comparator. So what we have did? First we did the single bit comparator operations. Then we are taking the AND gate and OR gate combinations based on our requirement. Okay. Right.